Let's do some full examples that involve the Heaviside step function. So just to remind ourselves of our two transforms that have to do with the Heaviside step function, if I'm taking the Laplace transform of a Heaviside step function times another function, in other words, this f of t is being switched on at a, then the Heaviside, or the Laplace transform of that is e to the minus as, that's the Heaviside step function, times the Laplace transform of the shifted f of t. Now all our shifting, we shift backwards and we shift forwards. We shift plus a to get into the Laplace world, we shift minus a to get out of the Laplace world, but all our shifting happens in time, in the real world. So when we go in, we shift time t plus a and then take the transform. When we go out, then we'll be unlaplacing things with e to the minus as, that's going to turn into the Heaviside step function, times some function of s. We unlaplace, we take the inverse Laplace, the e to the minus as becomes the Heaviside step function, and the function that's turned on, well, capital F of s would normally unlaplace to be little f of t. But we have to do our shifting in the real world in time. And the way to remember this is the argument inside the square bracketed piece, the part that's multiplied by the Heaviside step function, is equal to the argument inside the Heaviside step function. So it's t minus a here, it's t minus a there. In both cases, in and out we shift. In we shift plus a, out we shift minus a. The shifting always happens in time, and the out Heaviside step matches the argument inside the square bracketed piece, the part that's switched on. Let's do our example. So here I've got linear second order constant coefficient of y prime prime minus y equals this f, and here's this f then. It's 1 before 3, and then it switches to t. So what really happens then, we got to take this, we got to put the 1 before 3, and now I need to turn off the 1. So if I just stop like that, that's going to be, this piece here is going to be 1 before 3, and it's going to be 0 after 3. Now I'm going to turn on the t. I always put it in a square bracket because it's going to make it easier coming out. And some people will collect these together into one function. Make this u of t minus 3 all times t minus 1. You could do that, but I'm going to leave that. So what I've really said then is that these two pieces are the same thing. So now I can take the transform, the Laplace transform of this piece using our rules. So let's do that. I'm going to take the Laplace transform. So remember, this t minus 3 is a argument. It's the argument of u. This u of t minus 3 piece, that whole highlighted piece, is either 0 before times equal to 3, or it's 1 after times equal to 3. This t, though, is a function, the function getting turned on, is being switched on at 3. Let's take our Laplace transforms. Laplace transform of y prime prime, that's going to be s squared f minus s times y naught minus y prime naught. So what I've got down here is the Laplace transform of y prime prime. Now I need to go minus the Laplace transform of y, and we're using the notation that the transform of little y of t is big F of s. So there's transform. We transformed the left-hand side. Let's transform our right-hand side with the Heaviside step functions. The transform of 1 from our chart, 1 over s. The transform of just plain Heaviside step function minus the, which would be e to the minus 3s. Now I need to transform a function turned on, so I'm using this in rule. This Heaviside step function then goes to e to the minus 3s. And now inside the square bracket, I'm not transforming t, I need to transform the function t shifted over. So I'm transforming t plus 3. Everywhere there was a t, I put a t plus 3 first, and now I'm going to transform it. So I still need to just work on this last piece here. Transform of t plus 3 is going to be the transform of the t is 1 over s squared is 1 over s squared. And now I need to transform to 3, which is just 3 over s. Now I'm in the Laplace world, using I use this transform in rule. Now some things have an e to the minus 3s on them. They're the things when I collect on the way out are going to have the Heaviside step function on them. But my plan is going to be the same here. I need to solve this for f. I need f equals. So everything without an s, without an f, like this, like these pieces here, need to go over to the other side. So I'm going to go plus 2 when I move this minus 2 over to the other side, and a plus s when I move this minus s over to the other side. Now all the pieces with an f are on one side. I'm going to factor the f out. And this s squared minus 1, that's a familiar piece of algebra that looks like the auxiliary equation that I would have gotten if I would have done this with the auxiliary equation eigenvalue kind of way. I expect eigenvalues of, if I get an auxiliary equation of lambda squared minus 1, that'll factor into lambda plus 1 times lambda minus 1. I'll get eigenvalues of plus or minus 1. I expect to have pieces in the solution, some number e to the minus t plus some number e to the plus t. That's what I expect to have. Let's clean this up. So what do I mean by that? Well, let's put these pieces that have an e to the minus 3s together and factor out, just have the e to, so this minus 1 can go in the bracket here. So now I have this e to the minus 3s times something. That's going to untransform to be the function that is multiplied by the Heaviside step function turned on at 3. The rest of these things, let's put them all together. The rest of these things I'm going to untransform like normal. Now there's some cleanup before I solve for f. It's going to be nice. It's going to be algebraically convenient because I'm going to end up having to do partial fractions on some of these things. If we would just sort of put all these together before we do partial fractions. So I'm going to combine these fractions together into one piece. So common denominator is going to be s squared. So I'm going to need to multiply top and bottom of this 3 piece, and that 1 is going to be s squared over s squared. So that I can put all these pieces together as a common denominator here. So that's, let's see if I just hit simplify. Is it going to help me? Yeah, kind of. We'll do that in a minute. All right, so I've just put this together into one fraction so that when I divide out this s squared minus 1 bracket, it'll go on the bottom, and then I'm set up to do partial fractions once, instead of, if I would have put it underneath here and here and here, I would have had to have done partial fractions 3 times. In the same regard, we can clean this up here, common denominator of s. Will it just simplify for me? Yeah, it does. So that'll be that's just putting those pieces together in one fraction, because I think it'll help me out later. Now I'm going to solve for f. That means dividing everything out by this s squared minus 1 bracket. So it gets on the bottom here, and it goes on the bottom here. Notice I'm keeping this e to the minus 3s tacked on the outside of that square bracketed piece, because I want to use this getting out rule. So everything that has the e to the minus 3s is going to turn into the Heaviside step function. So I want to keep it organized. Now let's clean this up some more. This s squared minus 1 will factor into s plus 1 times s minus 1. So if I do factor it, then let's factor it. If I do factor it, now I can see that one of these s plus 1s and this s plus 1 can cancel. So that makes my partial fraction simpler. Maybe I can factor this piece and cancel something on the bottom. If I can and I don't see that, the math will take care of it when I do the partial fraction. So let's leave that. Now, need to break this up into partial fractions. The outside one is going to be some number over s plus some number over s minus 1. Partial fractions will tell me the a and the b. Inside the square bracket, I'm going to have, I've got a repeated factor and this s squared minus 1. Remember, we can factor that into s minus 1 times s plus 1. So this is going to have 4 factors. I'm going to have a number over s plus repeated factor, a number over s squared plus a number over s minus 1 plus a number over s plus 1, and I got to do over s plus 1, and I got to do partial fractions to figure out all these a, b, c's. Now this a and this b are not the same as this a and this b. I'm just doing I'm just keeping the letters in order, and I'm going to use them separately. Now we do partial fractions to find out the a and the b and the c. Okay, so I did partial fractions and I found the a and the b and the c and the d, and yeah, like a cooking show when they pull something out of the oven already done. That's, you know, that took like a few minutes to figure that all out, but we've broken that up. Now I'm set to un-Laplace this. So let's take the inverse Laplace. The inverse Laplace of capital F of s then is just y. The inverse Laplace of minus 1 over s is going to be minus 1. The inverse Laplace of 2 over s minus 1, that's 2 e to the t. Now we're set to un-Laplace the piece with the Heaviside step function. This e to the minus 3s then is going to be that Heaviside step function turned on at 3. Now all this stuff in the square bracket, normally the stuff in the square bracket, the minus 3 over s would un-Laplace to be minus 3. The minus 1 over s squared would un-Laplace to be minus t. The 3 halves e to the minus s would un-Laplace to be inverse Laplace to e to the t and the 3 halves over s plus 1 would un-Laplace to be 3 over 2 to the minus. So this is what the piece inside, this is what the square bracketed piece would un-Laplace to be on its own. But I want the argument, the t's in here, to match the argument inside the Heaviside step function. So I'm not just taking that piece, I need to shift time. So everywhere there's a t, I need to put a t minus 3. So this t is going to become t minus 3 in the bracket. This t is going to become t minus 3. This t is going to become t minus 3. And I got to be careful here with the bracket because that'll be minus all t minus 3. Now this is the final solution then to our linear second order differential equation with a Heaviside step function in it. Alright, there's a lot there in that first example, so let's do a second example. Now this one's second order as well. This one could be a spring question because all the coefficients are positive, right? The mass could be 1, the coefficient of friction could be 2, and the spring constant could be 1, and this would be like a forcing function where someone's forcing on the spring for the first second, you know, increasing from 0 linearly 0 to 1 and then letting off. It would be initially at rest at equilibrium. So the first thing we're going to need to do is write this forcing function as a Heaviside step. So it's t, and now I need to turn that piece off. So minus t minus 1 times t. So for time less than 1, this u is going to be 0, so it's going to be t minus 0 times t, or just the t like I want. For time after 1, this u of t minus 1, this is going to be 1, so it'll be t minus 1 times t, 0. Let's take the transform then. The transform of y prime prime are s squared f minus, both coefficients are 0, so minus s times 0 minus 0, plus 2 times the transform of y prime s f minus 0 plus the transform of y f is equal to. So with the two initial conditions of 0, I can see I'm going to factor the f out here and I'm going to get my auxiliary equation. Transforming, or a piece that looks like my auxiliary equation. The transform of t, 1 over s squared. Now I'm going to transform the Heaviside step function. So e to the minus s times 1. And everywhere there's, I got to shift first. Everywhere there's a t, I got to put a t plus 1. So I'm now transforming not t, but t plus 1. And the transform of t plus 1 would be 1 over s squared for the t, squared for the t, plus 1 over s for the 1. So now I'm in the Laplace world. I've taken the transform. My steps are going to be the same as always. I'm going to now solve for f. It's going to be f times, well, f times our, what looks like our auxiliary equation. Let's put these fractions together here. So common denominator is s squared, so this will be like 1 plus s on the top. So I've just common denominator, put those fractions together. Now, oh, note to self, this s squared plus this factors into s plus 1 all squared. So when I solve for f, dividing this by s plus 1 all squared, and now on this piece here, one of those s plus 1's will cancel this top, so that'll make my fraction easier. So now I've solved for f. My next step is going to be break these two pieces up into partial fractions and then unLaplace them. So the two pieces, I need to break this piece up with partial fractions, this piece up with partial fractions. So let's do that. Okay, so I've broken those two pieces up into partial fractions, and now we're set to unLaplace. Unlaplace the f is y. Unlaplace 2 over s plus 1 is going to be 2 e to the minus t plus, oh, this is going to unlaplace to be t e to the minus t. Actually, I'm not surprised that I get these two pieces. If my auxiliary equation would be lambda squared plus 2s, or 2 lambda plus 1, I would have got eigenvalues repeated, minus 1 and minus 1. I would have had an e to the minus 1 times t and a t e to the minus 1 times t. There's my homogeneous solution part there. I'm not surprised I get that. 2 over s and the inverse Laplace of 1 over s squared. Now my Heaviside step function, and now I'm set to unLaplace the stuff inside the square bracket. Remember, the argument of the stuff inside the square bracket, the function that gets turned on by this Heaviside step, has to match. Everywhere there's a t in here, I have to write a t minus 1. So this 1 over e to the 1 over s plus 1 is going to end up being inverse Laplace to e to the minus t. But everywhere there's a t, I got to put a t minus 1. Careful with the brackets. The minus, or the minus 1 over s is just the minus 1. There's no t there to plus. Normally 1 over s squared would be t, but I got to put t minus 1. And here's the solution to this differential equation. notice, let's check this out. This is a quick and easy way to make sure, or at least not to prove that my answer is right, but to at least check to see if it's probably right. If I make t equal to 0, I'm supposed to get 0 out. When I make t equal to 0, I get 2 plus 0 minus 2, so 2 minus 2, that's 0, plus 0. For times less than 1, like 0, this Heaviside step is 0, so this whole square bracketed piece is blanked out by the 0. So when I make t equal to 0, long story short, I get 0 out. If I were to differentiate this, I really don't have to worry about this piece here because it's always going to be, at time equal to 0, it's always going to be equal to 0. If I differentiate this, I'll get, I'll let you do this. If you differentiate this and check, you will get also 0. Now, that's checking if this piece, the part that before this Heaviside step switch is right. How do I check if the, the piece inside the square bracket, the part that gets switched on by Heaviside step, how am I sure that that's correct? Well, it should go smooth. In other words, the switch comes on at 1. So when I make t equal to 1 in the whole piece, it should, if I make t equal to 1 before the switch, so right times right before 1, where this u is still 0, I'll get a value. And for times right after 1, where this u is 1, I'll get a value. They should be the same value. I guess in calculus, the limit from the left approaching 1 should equal the limit from the right approaching 1. It should be a continuous function there.